Okay, so here's our last online lecture for the 9591 course. And here we're going to talk about missing data and multiple imputation. Just so we're all on the same page, I want to talk about different types of missing data that we could have. One possibility is that we have what's called unit missing data, and this is where an observation is missing entirely, right? We call somebody and they either hang up or don't answer. In a sort of purely simple random sample, that person would be one observation with all missing data. We also have when they have a missing value. So when a particular question isn't answered by a respondent, but that respondent is otherwise participating in the survey. So they answer most questions, but some they don't. So those would be missing values. And missing waves would be unit missing data, but for an entire wave of a longitudinal study. We're going to focus here entirely on just missing values. Those other two problems are much more complicated to solve, and so we're not going to propose to solve those, but we're going to concentrate on missing values. So the first question is, why do we care about missing data at all, right? Why do we have to worry about it? The software that we use automatically does something with it, right? And it does what's called listwise deletion. But what we'll see is that listwise deletion can actually cause problems for us. So if the missingness is systematic, listwise deletion can cause bias in our results. It can also reduce the sample size, where it might make reliable inferences more challenging. And systematic missingness can truncate the sample, calling into question the generalizability of the results. And while it has been practice for as long as we've been doing quantitative social science to listwise delete data and not worry about it, there are lots of ways of dealing with this problem, and being proactive is a good way to sort of signal virtue to reviewers. Okay, I want to sort of drill down on a couple of these ideas. Missing data, not only does it cause sort of statistical problems, it can also cause problems at the level of theory building and testing. So if science is an enterprise where useful theories live and unuseful theories die based on an accumulation of knowledge, then this can cause two problems. The first is that in areas where the same flawed research design propagates, then the result of continued iterative improvement is only to find a local maximum. So that is, if we're all using a sort of bad way of doing research, then the result that we get from iteratively improving on our bad research design is not necessarily the truth that we're looking for. And when studies with missing data show weak relationships, theories might be in danger of being dismissed when, if we had the complete data, they would support the theory. So these are both good reasons to think about dealing with missing data in an appropriate way. So Rubin has the most prominent classification of missing data that people use today. And essentially there are three types of missing data. There are data that are missing completely at random, data that are missing at random, and data that are missing not at random. And this classification scheme is based on the variables that have the missing data, the associated variables, that is, other variables in the model that maybe do or don't have missing data, and a hypothetical mechanism underlying why the observations are missing to begin with. To develop Rubin's classification, we first need to define a few different terms. The first is this matrix that we call R. So this is a matrix of dummy variables that mirrors the data matrix, where we have 1 indicating a missing value and 0 indicates any non-missing value. So if we had our usual data frame, right, where let's say we have x and y, like this, we could make an R matrix that had the same elements, but 0, 0, 1, 0, 0. But that looked like this. So these missing values show up as 1s, but any non-missing entry shows up as a 0. We refer to Y as our data matrix that we can sort of partition into two pieces. Y observed, which identifies the observed values, the non-missing values in Y, and Y miss, which are the missing values. Now, if we go back to thinking about the data that we had before, if we go back to thinking about our data, we had it like this. So we had it like this. The idea is that it's not that this observation simply doesn't exist in reality. It's that we were unable to measure it, right? We were unable to measure it because the relevant information wasn't available to us, or the person who knew the information failed to respond to that question. But it's not that the data, it's not that in reality the data are missing, it's that we failed to measure it. So the Y missing isn't this actual missing value itself, it's the true value of that variable out in the world, right? So we assume that all of the variables that we have some true value out in the world, and Y miss are the true values that would have been observed if we had been able to perfectly observe the data. We also have this term phi. That's the relationship of the observed variable matrix and the missing variable matrix to this dummy variable matrix R. Right, so this tells us how the observed values that we see help us predict R, and the missing values that we don't see would have helped us predict R. Phi is a purely theoretical thing here because we don't know the values in the Y miss matrix, and thus we can never actually calculate phi, but it gives us a way of thinking about what kind of missing data we have. So the first case is when phi equals 0. That is, there's no relationship between what we observe and R. That is, we can't predict why observations would be missing based on what we observe. And also, there's no relationship between R and the values that we don't observe, right? So if we could have observed those, there would still be no way that those would help us predict which observations would be missing or not. And these data are called missing completely at random. So if we're thinking about the mechanism that generates the randomness or the missingness, it's just randomness, right? It's just flipping a coin or rolling a die or something like that. The data are called missing at random, or MAR, if there is a relationship between R and the observed values. That is, the things that we do observe help us predict when an observation will be missing or not. But there's no relationship between R and Y missing. That is, the stuff that we don't observe is completely unrelated to whether an observation is missing or not. The data are missing not at random when there is a relationship between R and the missing values themselves. So this would happen if somebody didn't answer the income question because they thought their income was too low, and saying it would be socially undesirable. So those sorts of problems are when we have missingness not at random. It's worth noting here that it basically doesn't matter what the relationship between R and Y observed is here, because so long as there's any relationship between R and the missing values, we're in this classification, regardless of what other attributes exist. So the property ignorability is a property of missing at random and missing completely at random data. The mechanism is ignorable if we don't have to model the missing data mechanism itself. That is, we could reasonably recover the information from other observable data that we have actually observed. We call data non-ignorable if they're missing not at random. So how do we deal with missing data? Well, the usual way that we deal with missing data is to listwise delete them. And this is the usual way because it's what our software does automatically. There are a number of imputation algorithms that would help us basically make a good guess at what the observed values would have been. One possibility is mean imputation, right? With mean imputation, we impute to all missing values the average value of that variable. You shouldn't do this for lots of reasons. The next possibility is regression imputation, where we build a model based on the data and we impute the missing values from that model. You probably shouldn't do this because this tends to produce bias in the standard errors. So it doesn't actually change the effect size as much, but it produces a massive downward bias in the standard errors. And ultimately, if you have any sort of complicated missingness, this will just simply fail. You wouldn't be able to do this anyways. Hot decking is another option. I don't want to talk about that as much, although there is a multiple hot decking algorithm. There's a package called hot.deck in R that I maintain that does multiple hot decking, but that's not what most people are doing these days. Instead, most people are doing multiple imputation, and we'll focus on this one for the rest of the lecture. So just to give you a sense of why listwise deletion is bad, listwise deletion involves deleting all observations that have at least one missing data point. So in the best case scenario, listwise deletion causes inefficiency because we lose observations. And in the worst case scenario, it can cause bias and inefficiency. Also, we're losing a lot of information because we have valid values on lots of variables, but with missing data on just one, we delete that whole observation. Oftentimes, from a mean squared error point of view, omitting variables with lots of missing data might be preferable to listwise deletion, though the things we're going to talk about in a bit are better. So I want to talk a little bit about what multiple imputation does, and then we'll talk about how we do it in R. First, we take our data matrix and we basically fill in, just with any kind of guess at all, values for all of the missing values. This could be just random. There could be random draws from the variable's marginal distribution. It could be with the mean. It could basically be anything. Then we move through our data set. Let's say we start with x1 and we predict x1 using all the other variables in the estimation model, including the dependent variable. Right? So we've filled in all of the missingness on all of the variables. What we're going to do is we're going to predict x1 with all of the other variables in the model. And we're going to fill in the missing observations, or the observations that we're missing on x1, with a draw from the posterior distribution. You could think of this sort of as the sampling distribution of x1. In fact, what basically really happens if we're using, this is one way of doing it. The other way, which I think is the default in the software that we're going to use, is to identify observations that have predictions that are really close to the prediction of the missing observation, and then use the observed value of x from those observations. So using the previously predicted values for x1, we move on to x2 and proceed in a similar way. Moving all the way through the data set, imputing all of the variables in the model. We start over again using all of the imputations from the previous period and try to improve on those. Right, so this is an iterative process that moves through the data several times, each time trying to improve the nature of the imputed values. And we do that until the model converges. That is, until we're basically drawing from the same set of points for every missing data point each time. Before we move on, it's probably worth noting well, two things. One is we do this several times, right? So what we're going to end up with after we complete this procedure is one imputed data set. But the whole point of multiple imputation is that we actually have to go through and make a bunch of imputed data sets, right? And in each one, the data that we originally observed will be exactly the same. But the imputations will be different because the process of imputing is a stochastic one. It's one where we're taking draws from either a distribution or some set of candidate values from other observations. So we end up with at least 2, but usually somewhere between 5 and 10, and we might be better off with somewhere between 50 or 100 imputed data sets, right? So that's one. The second thing that I want to mention before we move on is that multiple imputation's goal is not necessarily to guess what the right answer would have been, right? So we're not trying to make one data set with the best possible guesses that we can get. What we're trying to do is characterize the uncertainty in our models that result from having not observed all of the observations, right? And that's where the multiple imputation comes in, right? By having variation in the imputed values across data sets, that lets us characterize the uncertainty that arises from having missingness. And so our model parameters are not only unbiased, but now we get standard errors that are approximately right because we've taken account of all of the sources of uncertainty in the model, not just sampling variability, but also variability that comes from missingness. So like we said, with multiple imputation, we impute more than or equal to 2, but usually somewhere between 5 and 50 completed data sets. And in each one of those completed data sets, we estimate the model that we're interested in. So we get 50 coefficients and 50 variance-covariance matrices of those coefficients, assuming that we've generated 50 completed data sets. So here, Q with a T superscript these are the parameter estimates from our model. For example, those could be regression coefficients. And so we're defining Q bar here simply as the average across all of the models of those coefficients. So the T superscript here identifies the imputation round. So if we have 50 data sets, there'll be 50 different imputation rounds. So Q bar is just the average of all of the individual Qs. So if these are regression coefficients, Q bar would be the average of, say, the age coefficient across all of the imputed variable or the imputed data set models. U is the variance covariance matrix of the estimators in each model. And U bar is simply just the numerical average of each of those matrices. So it's basically an element-wise average, which means that so for the variance of the first parameter, we would simply average all of the variances of all of the first parameters. We then can identify or define this B term. And this is the empirical variance of the model parameters. And what we mean by that is that we are simply taking all of the Q terms across all of the imputed data models, and we're finding the variance of those terms. U and B, or U bar and B, are both components of the overall variance. T, which we can define as sampling variability, right? So this is sampling variability, plus B, which is imputation uncertainty. Note that if we had completely observed data and we did this 50 times, B would be exactly 0, because every value of Q would be exactly the same, right? The coefficient for age in our model would be exactly the same every time because we had completely observed all of the data. So to the extent that that's not the case, this increases the variability that's in our model because we're uncertain about what the values that are in those underlying terms, and multiple imputation has allowed us to calculate and characterize that uncertainty. You'll note that the fewer imputations we have, the bigger the weight on this B term relative to the U bar term. But that goes down, 1 over m will, or 1 plus 1 over m will approach 1 pretty quickly as we increase the number of imputations. There's one other measure that we can calculate that we'll actually see in the output later on, and that's the fraction of missing information. This is a measure of how uncertain we are about the values being imputed for the variables with missing data, and how that uncertainty sort of propagates through to our model parameters. So the fraction of missing information requires us to know two things. Are the fractional variance increase due to missingness? So this is 1 plus 1 over m, which is the number of imputations. B, remember, is imputation uncertainty. And U, which is sampling variability. So that's the fractional variance increase due to missingness. The degrees of freedom then are m minus 1 times 1 plus 1 over r squared. We can then define the fraction of missing information this way. It's not super important that you understand why these are what they are, but only that you understand that the fraction of missing information tells us something about the uncertainty underlying our imputation procedure. So a bit of advice before we move on. First, all of the variables in our model, including the dependent variable, should be in the imputation model. There's a bit of a debate about this in political science, or has been, about whether the dependent variable should be in the imputation model or not. I've tended to come down on the side where it should. If we're imputing one thing, we should be imputing all of the things. But there are people who would suggest otherwise. Extra variables can be included in the imputation model. So if we're trying to impute an x variable, it might be that there are other variables that don't relate to y, but that do relate to x. And even though we may not have those in our ultimate predictive model for y, we may want to have those in our imputation model so we get good imputations of x. This is a situation that we would call super efficiency. Because the imputation mechanisms are built on parametric statistical models, if there are any nonlinear trends that need to be incorporated, then those have to be in the imputation model as well. So this would be things like polynomials or transformations. So if we had a variable like population, we would probably want to log it before we imputed it. And the conventional wisdom is that 5 to 10 complete data sets are usually sufficient to generate a result. More recent work suggests something like 50 to 100 is a lot better, though. And the real important point here is that we only should have to do the imputation once, right? We generate one set of imputations, and then our model building exercise proceeds after that. So we don't have to redo the imputation model for every model that we run trying to predict y. So the default method for numerical data in the imputation procedure that we're going to use is called predictive mean matching, and we talked a little bit about that already. There are also a suite of GLM methods. So there's norm for continuous data, log reg for binary, polar for ordinal, and polyreg for that does a multinomial model. We're not going to talk about these much, but there are machine learning algorithms in here too. So classification and regression trees and random forests are also possible ways of doing imputation. Here's an example using the MICE package. So MICE stands for multiple imputation by chained equations. And that's sort of the default way of doing imputation in R. So here we're reading in some data from the ANES. We want to make sure that the factors are actually coded as factors in the data. And then the first thing we're going to do is we're going to estimate a model. So here's our listwise deletion model. Nothing sort of super remarkable about that. But I want to show you how the imputation works. So here, you want to make sure to subset your data. So it only includes the variables that you want to be imputed. This can be a sort of lengthy procedure, and so you don't want it to be imputing a lot of data that you don't need. M is the number of observations, or the number of imputed data sets that we're going to generate in the end. In real life, we should probably have this be 50 to 100. Just to make it run faster, I just did 5 for right now. There are some, in the MICE package, there are 2 functions, lm.mids and glm.mids, that estimate linear models and GLMs on multiply imputed data. So the pool function here takes a bunch of models and then uses Rubin's rules to combine them. That's what we talked about before. And then summary generates a summary of the models. So here you can see we get the sort of usual model summary. And this actually also tells us the degrees of freedom term. right, which is a function of that fractional increase in variance due to missingness that we talked about a little bit before. Probably what you'll do, though, is to use the MIcombine function that's in the MItools package. This allows us to combine estimates from a lot broader set of models. The first thing that we're doing here when we make D is we're completing the data set. So we're essentially looping over the values 1 to m, and we're using the complete function, which generates a complete data set for our mice object. And since I is the counter here, we're just sticking in a different number each time, right? So the first time through it will be 1, the second time through 2, and so forth. So D will be a list where each element of the list is a completed data set. Then we're generating an object called mods, and we're going to use lapply, so that's a list apply to D. So since the data set is a list, we can use that as the first argument to lapply. And then what we're going to do is a function to each element of D. Each element of D is going to be identified in the function as x. And so we're going to run a linear model of left, right on age, education, male, and household income, where the data is equal to each of the completed data sets. And we can use MIcombine basically to pull all of those models together. And summary will give us a result that pulls all of those results. And we also get, in addition to coefficients and standard errors, we get a 95% confidence interval. And we also get the fraction of missing information that we talked about before. You can see that this ranges a lot from like 10% here to almost 45% here. Now, this is not a function of the number of missing observations. It's a function of how uncertain or how much extra uncertainty there is in the parameter estimates as a function of having missing data. One other thing we might want to do with our models is to create an effects plot. Now, the effects package doesn't work with the results from MIcombine, but there's a function in the R code for the slides called MakeMIMod, and what that does is it goes through these 6 steps. What it really does is it makes a sort of fake one model object that has all of the right stuff in it from our imputation model. So what this will do is it will build an object that will basically trick the effects package into thinking it's working on a single-shot GLM, when in fact all of the stuff inside of it comes from our multiple imputation model. So here's an example of how that works. We load the effects package. We use the MakeMIMod function. So the first argument is a formula, the formula that we want to estimate. The second is the mice object. And the last element here is the model that we want to run. There's also another, I have to look to make sure, but it's model args. So there's another possible argument here, model args, which would allow you to make a list of other arguments that get passed down to the model. And here, using this new object that we created, we can make an effects graph pretty easily that has basically all of the right information in it. The other tools that we have learned from the DA-MISC package, and maybe and probably the CAR package too, will all work here on this kind of object. So you've got lots of options in trying to figure out what to do. If you're thinking about presenting these results, you need to present the same things that you have presented all along. So you need coefficients, standard errors, and some flag for significance. You also may want to put the fraction of missing information in. That's another sort of diagnostic tool that you can put so people can use. You also would want to discuss the multiple imputation method that you used. What assumptions did you make? What variables were in the imputation model? Did you impute the dependent variable? How many imputed data sets did you use? So basically, all of the details of the imputation mechanism should also be discussed so people know how to evaluate the results that you found.